Welcome back to the deep dive. Today, we're getting into something pretty fascinating, findings that might make you look a bit differently at how our top reasoning models actually, reason. You know how we keep seeing these LLMs just crushing complex problems? Well, it turns out a recent paper found a sort of Achilles heel, and it's with seemingly simple, ill-posed questions.
Yeah, it's a bit like that deep thought computer in the Hitchhiker's Guide, giving the answer 42, but not really connecting it back to the actual question.
Exactly. This research highlights this really odd kind of overthinking in these advanced models.
That's right. So in this deep dive, we're digging into the paper, Missing Premise Exacerbates Overthinking. Are reasoning models losing critical thinking skill?
It's intriguing.
Yeah, and for all you AI researchers and ML engineers listening in, and I know that's a lot of you, we're going to unpack their main discoveries, the whole experimental setup they used, and what this MIP-Overthinking, as they call it, really means.
MIP-Overthinking. Got it.
And it's not just some small quirk, apparently.
Right.
It might point to some, deeper limitations in how we're building AI right now.
Okay, so let's do that quick summary first, the kind of thing you can share quickly. Basically, reasoning LLMs kind of freak out when they see questions missing key info, what the paper calls a missing premise, or MIP.
Right, they freak out, their response length just explodes. We're talking 2 to 4 times more tokens sometimes.
2 to 4 times?
Yeah, leading to this super inefficient, unproductive MIP-Overthinking. But here's the kicker.
What's that?
The non-reasoning models. They actually handle these bad questions better. Shorter responses, and they often spot the missing info more easily.
Huh. That's unexpected.
Totally.
Yeah.
It really suggests that the way we're training these powerful reasoning models, it might not be encouraging efficient critical thinking like we thought. Okay, so let's unpack that. What is a missing premise problem exactly? And how does it cause this MIP-Overthinking?
Yeah, let's define that first.
Sure. So the paper gets a bit formal, but think of it like this. You have a question, Q. That's some facts. The premise is P. Normally, there should be just one right answer, A, that you can logically get from P to solve Q.
Makes sense. FPQ equals A, basically. One unique A.
Exactly. FPQ is a set of answers, and normally FPQ 1. A missing premise problem happens when you start with a subset of premises, P prime, that's missing something crucial from the full set P.
Okay, so P prime is incomplete.
Right, and with that incomplete set P prime, you don't get a single unique answer anymore. So FPQ is not equal to 1. That missing piece was absolutely essential for finding the solution.
Got it. So it's not just a hard question, it's fundamentally unsolvable because something's missing. And that's what triggers this MIP-Overthinking, which you said is different from just general overthinking.
Yeah, good distinction. General overthinking is like when a model writes a super long essay for a question that is solvable, but the extra length doesn't really help.
Right, just unnecessary waffle.
Exactly. Maybe overthinking is specific to these ill-posed questions, the ones lacking that key info. The paper gives a great example using GSMAK math problem.
Yeah, the sprint example.
That's one. The original is, James runs 3 sprints 3 times a week. Each sprint is 60 meters. How many total meters? Totally solvable.
Yep, simple multiplication.
But the MIP version, James runs 3 sprints 3 times a week. He runs. Uh-oh. Distance per sprint removed each sprint, total meters.
Okay, I see. You can't solve that. The distance is gone. It's impossible to get a number.
Precisely. And the paper's big finding is that reasoning models, faced with this, don't just say, hey, info missing. They often launch into these crazy long reasoning attempts.
Instead of just stopping.
Exactly. Figure 1 in the paper shows this really well. A reasoning model like DeepSeek R1 gives a neat answer for the normal question, but for the MIP version, the token count just skyrockets. It goes off on all these tangents.
Wow. And what about the non-reasoning models in that figure?
Well, the figure also shows like a simple query, what is the value of A? A non-reasoning model like Gemini 1.5 quickly says, you haven't defined A, or asks for more info.
It recognizes the gap.
Right. But DeepSeek R1, again, it goes on this long, rambling path before giving a nonsensical answer. It really highlights that these reasoning models seem to lack that critical skill to just say, hold on, I can't proceed here.
Okay, so they didn't just rely on 1 or 2 examples, right? They built whole data sets to study this systematically.
Oh yeah, absolutely. They're quite meticulous. They put together 4 different MIP data sets, each designed to test this from different angles, different difficulty levels.
Tell us about them. What was the first one?
First was MIP Formula. This was a synthetic 50 formulas they generated using rules, mixing variables and operators. The key thing, every formula had at least one variable that wasn't assigned a value.
So fundamentally unsolvable, like asking for x plus y without defining x or y. Very direct.
Exactly. Very controlled way to introduce MIP.
Okay, what was next?
Next up was MIP S vampy. They took the S vampy data set, that's elementary school math problems, and did something clever called body question swapping.
Body question swapping. What's that?
They'd take the main text, the setup from one problem, and pair it with the actual question from a different problem in the data set.
Huh. So the information given doesn't actually match what's being asked, like a setup about apples and oranges, but the question is about bananas.
Pretty much.
Yeah.
Creates these logical mismatches. They made 300 of these flawed pairings for MIP S vampy.
Okay, that seems like something a person would probably spot fairly quickly. What about harder problems?
Right, so then they made MIP GSMAK. They took 582 questions from the GSMAK benchmark. These are trickier multi-step math word problems.
More complex than SVMP. Yeah.
For these, they used essential premise removal. They carefully analyzed each problem, found the 2 or 3 numbers absolutely needed for the solution, and then just deleted one of them.
Ah, like the running example again. Removing the distance per sprint.
Exactly like that. And they even had humans check these modified questions to make sure they really were unsolvable because of the missing bit.
Good check. And the last data set, you mentioned 4.
The last one was MIP Math. This was the toughest. They took 58 problems from the Math 500 data set. These are hard, math competition level.
Okay, really pushing the complexity.
Yeah. And because they're so complex, they had to manually go through each one and figure out which premise was truly essential and then remove it. Took some deep math understanding just to create the MIP versions.
Wow. So a really varied set of challenges, from basic logic flaws to subtle missing info and tough problems. Seems comprehensive. So they have the data sets. How did they actually measure the overthinking? What were the metrics?
Good question. They mainly used 3 key metrics. First, the obvious one, response length.
Just the number of tokens?
Yep, average tokens per response. A direct measure of how much more the models are, let's say, writing, if not thinking, for MIP questions versus normal ones.
Makes sense. Longer response, more processing, potentially overthinking. What else?
Second, the abstain rate for MIP questions. This is crucial. It's the percentage of times the model actually said, hey, I'm missing information I can't answer, or ask for clarification.
Right. A high abstain rate would be good here. It shows critical thinking.
Exactly. It shows the model recognizes the limitation.
And the third metric?
Third was accuracy for well-defined questions. They needed a baseline. They wanted to make sure that any weird behavior on MIP questions wasn't because the model just got worse overall.
Ah, okay. So check if it can still solve the solvable problems correctly.
A control measure.
Precisely. So you measure accuracy on the original complete problems too.
Okay, response length for overthinking, abstain rate for critical recognition, and accuracy on normal questions as a control. Got it. Let's get to the juicy part. What did they actually find? What were the main results?
The main finding, and it's pretty stark, is that reasoning models consistently generated way longer responses for MIP questions, like 2 to 4 times longer in terms of tokens compared to the well-defined versions.
2 to 4 times. That's huge. It is. Figure 2 in the paper shows this clearly for MIP GSMAK. Models like QWQ32B, DeepSeek R1, their token output just surged on those incomplete problems.
And this is compared to their already fairly long reasoning on the standard GSMAK problems.
Exactly. But here's where it gets really interesting. They compared this to the non-reasoning models.
Right. What did they do?
Also in figure 2, you see the non-reasoning models kept their response lengths much more stable, whether it was a normal question or an EVA-NIB one. Sometimes they were even shorter overall on the normal questions than the reasoning models.
Huh. So the reasoning models seem hardwired to just expand when confused, while the others are more consistent.
It kind of looks that way. It suggests the very thing that makes them good at reasoning might also make them prone to this overthinking on flawed inputs.
So they're thinking longer, writing more. Did it at least help them realize the premise was missing? Did the abstain rates go up for reasoning models on MIP questions?
That's the really surprising, maybe worrying part. No. There was a clear lack of correlation between that huge increase in response length and any real improvement in abstain rates for the reasoning models.
So more work didn't lead to better recognition of the problem.
Pretty much. It directly contradicts that idea of test time scaling, where more computation usually means better results. Here, it just meant more words, not more insight.
Wow.
Figure 2 shows that some reasoning models were slightly better at abstaining than others, but many, despite all that extra processing, still just failed to identify the missing premise and tried to answer anyway.
That feels like a major finding. All that computation essentially wasted because it didn't lead to the right meta-conclusion. This question is flawed. What about accuracy on the normal solvable questions? Did the reasoning models at least justify their length there?
Well, Figure 2 does show a slight accuracy improvement for reasoning models on the well-defined GSMAK questions compared to non-reasoning ones. So the extra steps help a bit when the problem is solvable.
Okay, a small gain.
But the paper argues that this tiny gain comes at a massive cost. This huge, unproductive overthinking and failure on the MIP questions. And Table 2 hammers this home across all the datasets. Formula, SVMP, GSMAK, Math.
Same pattern everywhere.
Consistent pattern. Reasoning models equals longer responses, much lower abstain rates on MIP questions. Interestingly, on the really hard MIP Math set, all models tended to get longer and abstain less. Suggests spotting missing info gets harder as complexity rises for everyone.
Okay, so the evidence points strongly towards reasoning models overthinking MIP questions without actually recognizing them better. But what's happening inside that overthinking? Did they look at the reasoning steps themselves?
They did, yeah. Table 3 breaks down the kinds of words they use, like alternatively weight check, but hypothesis words, and also just a number of reasoning steps, specifically on MIP GSMAK.
And what did that show?
A massive jump. An explosive increase, as they put it, in both those reason-related words and the step count for reasoning models when they went from normal to MIP questions.
So they're doing more reasoning moves.
It looks like it.
Yeah.
But it suggests they're getting stuck in these loops, like constantly doubting themselves, revisiting the question, checking their knowledge, but not actually getting anywhere because that key piece is missing.
Like running in circles. Maybe it's this. No, wait, let me reread. What if? Because the core info isn't there.
Exactly that. And in contrast, the non-reasoning models often showed fewer steps for MIP questions than normal ones, maybe hinting they spot the unsolvability faster.
Interesting contrast.
And Figure 4 has this great example response from one model, S1.1-32B. They analyzed it and found these patterns recurring over and over, revisiting the question, visiting knowledge, proposing assumptions, self-doubt, pausing checking.
All happening excessively.
Totally overused.
Yeah.
Leading to this incredibly long, rambling, and ultimately useless response. It really visualizes the model getting lost.
That paints a clear picture. It's not efficient at all. You also mentioned step-level similarity analysis. What was that about?
Right. So they took the responses, broke them down into individual reasoning steps. Then they used embeddings, specifically all-mental LM L6v2, to calculate how similar each step was to every other step in the same response. Cosine similarity.
Okay, measuring semantic similarity between steps.
Yeah, and they plotted these as heat maps in Figure 3. The finding. For MIP questions, the average similarity between steps was significantly higher, and the variation in similarity was lower compared to normal questions.
Higher average similarity, lower variance.
What does that mean in plain English?
It basically means the model is repeating itself a lot. It's going over very similar ideas, rephrasing points without making much real progress. High similarities suggest redundancy. Low variance means it's consistently redundant, not exploring diverse paths.
So more evidence of being stuck in a loop, just rehashing similar thoughts without breaking new ground or realizing the core issue.
Exactly. It really highlights the inefficiency. It's like someone confused just saying the same thing over and over in slightly different ways. That's a great way to put it. Okay, this leads to a crucial question. Do the models ever suspect something's wrong? Do they have any inkling the question is flawed?
Yeah, this was a really cool part of their analysis. They used GPT-4o, actually, to read through the reasoning chains and see if the model itself ever expressed doubt or suspicion about the question being solvable.
So, looking for signs of self-awareness of the problem.
Kind of. They measured two things. In-process suspicion rate, did the model ever hint at suspicion during its reasoning? And first, suspicion index, how early on did that suspicion appear?
What did Table 4 show?
Surprisingly, most reasoning models do show suspicion. They often indicate fairly early on in their process that something seems off or information might be missing.
Wait, so they know or at least suspect something's wrong.
It seems so.
But then they still go on to generate these super long, often wrong answers.
Exactly. That's the disconnect. Figure 5 shows this perfectly with a Sankey diagram. High suspicion rates on one side, but very low final abstain rates on the other.
So the suspicion doesn't translate into action.
Precisely. They feel something's wrong, but they lack the mechanism or the confidence to act on it and just say, I can't solve this.
That seems like a critical failure, having the awareness but not the appropriate response mechanism. So why? Why does this happen? Did the paper suggest any causes for this MIP overthinking?
They did hypothesize a bit. One main idea relates to reinforcement learning, especially in RL-based models. They suggest maybe the length constraints during RL aren't quite right.
How so?
Well, the model might learn that longer reasoning chains often get higher rewards during training, even if that extra length isn't always needed or helpful. It could lead to a kind of reward hacking.
So the model learns longer response, better reward, even when shorter and abstaining would be the truly intelligent thing to do.
That's the idea. It inadvertently rewards verbosity over critical assessment or conciseness in certain situations.
Makes sense. And could this spread to models not directly trained with RL, like supervised, fine-tuned models?
They think so, potentially through distillation. They actually did an experiment to test this. They fine-tuned a Quen model using a small set of MIP responses generated by DeepSeek R1, which is known for this overthinking.
So teaching Quen, using examples of DeepSeek's overthinking.
Yep. And the results, shown in Figure 6, were pretty clear. The fine-tuned Quen model quickly started showing the same signs. Longer responses overall, a bigger length gap between MIP and normal questions, and crucially, a lower abstain rate on MIP questions.
Wow, so the behavior is learnable, transferable, even through supervised fine-tuning on bad examples.
It strongly suggests it is. It means the problem isn't necessarily isolated to just RL models. It can propagate through training data and methods.
That's a really important point. It suggests the way we generate training data or the implicit biases in our training objectives might be reinforcing this unwanted behavior across the board.
Exactly. The paper really flags that our current training approaches for reasoning models might be missing something crucial when it comes to handling these kinds of ill-posed, real-world-like scenarios.
Okay, let's try to wrap this up. What are the absolute key takeaways our audience of researchers and engineers should really hold on to from this deep dive?
I'd say the main thing is, our top reasoning models have this significant flaw with ill-posed, missing premise questions. They overthink them, dramatically longer responses, lots of redundant steps, but without getting better at actually identifying the flaw and abstaining.
And the non-reasoning models are sometimes better.
Surprisingly, yeah. Often shorter responses, sometimes better at spotting the issue. It really forces us to question if our training for reasoning is adequately building critical thinking skills, especially the skill of knowing when not to answer.
So what does this mean for the field, for people actually building these systems?
It's a call to action, really. We need to look hard at our training methods. How can we better incentivize genuine critical thinking? How do we encourage efficiency and the ability to recognize insufficient information?
Because just making models that can reason isn't enough if they waste huge resources on unsolvable problems.
Precisely. It's about building more reliable, practical, and efficient AI. If models spin their wheels on flawed inputs, that wastes compute and erodes trust. We need systems that are robust to imperfect information.
Absolutely. Okay, so here's something for everyone to chew on, a final thought. We've seen that these models often suspect a question is flawed early on, but they plow ahead anyway. What kind of new training signals, or maybe even changes to the model architecture itself, could we design to actually instill that critical stop and think ability to prevent this massive waste of computation?
That's the million-dollar question.
And maybe flipping it around.
Yeah.
What are the real risks if we deploy AI systems widely that can't gracefully handle ambiguity or admit when a problem is ill-defined? Definitely some critical things to consider for future research. This was a great discussion. Thanks for breaking down this paper.
My pleasure. Really interesting findings.